Yesterday at the end, we did this one with a conical tank. In example or practice number 2 is going to be the sand falling in a conical pile. So the cone will be facing the opposite way, just for reference. But like the setup of it will be very similar to this one. But to wrap up, yesterday we did this example with a ladder against the house falling down, and if I get ambitious enough, maybe I'll find that fail army video.
I thought you just said it's a house falling down.
Ladder falling. I don't know what I said. It's a ladder falling down a house.
So I haven't watched the video yet. I just copied everything down. So what does the DT stand for?
So it's the derivative. So basically, every variable is implicitly differentiated. So everything is done with respect to time. So it's like a rate of change. So dt is essentially the rate of whatever changing with respect to time.
Okay.
This is why you should listen.
So
I was in Bible class. I didn't.
She didn't have to.
Go with my AirPods.
So
Yeah.
I'll kind of go back and walk through this one because we got to do part B that goes with part A. So I'll kind of walk back through this one really quick. But basically, the ladder. This is where I told Josh yesterday, don't get smart with me. I was like, can the ladder change length? And he was
Right,
like,
but
why
she
would I
doesn't
get...
know that because she didn't listen.
I know. But I said, don't get smart with me. And he was like, why would I get smart with you? I said, because some people are like, well, ladders can be adjustable. Anyways, this ladder is consistently 25 feet long. So it's leaning against the house and it's sliding away from the wall at the rate of 2 feet per second. So the wall, we don't know how, well, we will end up figuring out some more information. But basically, pretty much everything, well, these we draw triangles. There's a few things, obviously like a cone, but it still has triangles within it, whatever. But we have the ladder here. This is like my house. So this is the wall and then the ground here. And so this one was how fast is the top of the ladder moving down the wall when the base is essentially like 7 feet like away. So this is 7 down here. So the way I always set up is I figure out what variables I have and then the derivatives of each of them. Thought they were listening to music in there. And so I put down like my known information and then what I'm trying to solve for. And then if something like isn't changing or can't change or whatever, or like when we do a volume problem because it's V equals whatever, oftentimes like obviously it's not like V squared. So when you take the derivative, you're not still going to have a V left. It's just going to be like dV dt. So in this particular case, because the length of the ladder wasn't changing, that's why I just put a giant X here because obviously it can't change. So we knew the distance from the wall was 7 feet. I found 24 by plugging into the Pythagorean theorem. It also happens to be a Pythagorean triple, but that's just minor detail. So we used the Pythagorean theorem to find that, and then we knew the length here. So basically, that's how we found all of those pieces. And then dx dt is the rate at which it was falling. So that was 2 feet per second, or it's like sliding away from the wall at that rate. And then it wanted us to know how fast the top of the ladder was moving down the wall. So that's the dy dt, because that's the association of the wall there. So then we take the Pythagorean theorem, but because the whole reason we pointed out that the ladder wasn't changing is because I can go ahead and straight up plug in 25 and square it to get 625. Then take the derivative, and now, if the ladder was changing lengths for some reason, obviously that would be a whole other factor in this problem. But if it was, we would have to leave it as L. But we take the derivative, so 2x dx dt plus 2y dy dt equals derivative, that's 0. And then we just basically move things around and look for what we're solving for. And so we ended up getting to the negative 7 over 12 is that rate for dy dt. Sometimes there's going to be multiple things that you're solving for. Sometimes it's just one. It just depends. And like this one, technically there are multiple things I'm solving for, but part B, like they did it as like a separate question. So, but going with that, this next question, consider the triangle formed by the side of the house, the ladder, and the ground. So basically same triangle I've already got drawn up there. Find the rate at which the area of the triangle is changing when the base of the ladder is 7 feet from the wall. So In this case, I don't care about the length of the ladder because what's the area of a triangle?
1/2 base times height.
Yep. So 1/2 in this case, we'll do x times y, just to be specific for our problem. So there's no L involved here. There's no, like, I don't need the hypotenuse value, so that's why I don't care about that. So I'll have x, y, and then I have area. Then I have dx dt, dy dt, and dA dt. So most of this information is staying the same. Obviously, x is still 7 feet. Y we found in the previous problem, 24 feet. dx dt was given in the earlier part, so 2 feet per second. Then dy dt was what we solved for in the first part, -7/12 feet per second. Now, do I really need area? Right. I don't really need it. So I'm just going to put an x there because when I take the derivative, I'm just going to have dA dt. So dx or I don't need a, just like I don't typically need volume when I'm doing those. Now, I could absolutely find it by plugging in x and y. And if you were so inclined, it would give you 84 feet squared. So
why don't you need it? Like,
because when I take the derivative of this equation, there won't be an a left. So I won't need to plug in the information. Like, I can find it. If I said, what's the area of this triangle? Like, yes, you could tell me. But it would be 84 feet per second. Or not feet per second. 84 feet squared. If I cared. But I just put an X there because I don't need that piece of information. And sometimes I'll go ahead and write the information down if I'm not sure if I'm going to need it. Like, I've obviously done these enough that I can typically tell, like, hey, I'm not going to need this. But nothing wrong with finding it and then just leaving it sitting there. But I usually just put an X if I know I don't need it. So dA dt is what I'm trying to find. So we take the derivative of this equation, which would be what with respect to t?
dA over dt is equal to 1/2. Do I keep the 1/2?
Yeah, so the 1/2 will be on both pieces, or you can factor it out.
Okay.
I would leave it on both pieces at the moment.
So 1/2. Do I keep the x or do it?
Well, it depends on what you're taking the derivative of first. Are you taking the derivative of x or y first?
Oh yeah, it's a product thing. 1/2 x. Oh, I don't know if I can do this.
1/2 dx dt times y plus 1/2 dy dt times x.
That was too much for me. Okay, that makes sense.
And I just like the dx dt, dy dt at the end, but it doesn't matter. The order you said it is totally fine. And then now I take and I plug in the information because I'm solving for dA dt, so I don't need to move anything around. So this is 1/2 times 24 times 2 plus 1/2 times 7 times, oh gosh, this is a weird one, -7/12. So that's 24 minus 49/24. And at that point, I would just use my calculator probably to get an answer. I mean, I could obviously get a common denominator and leave it as a fraction, but it's a weird fraction, so I would just...
So we always multiply like y would be by dx over dt, and then x would be over or times dy, like over dt.
Well, this was a product rule.
Or I just mean like when we're. So it's usually like if I'm just taking like in the one above like the derivative of x squared, that would just be. It would always be by like.
It'll be like you would normally take the derivative where you get your 2x, but because I'm doing it implicitly, this will be like when we did the, like, it was like 2y prime, like that. It's like that, but Josh asked yesterday, can I just write it as a prime? And I'm like, technically, like, in technicality, yeah, you could write it that way, but the official right way to write the answer would be to write it as like dx dt or dy dt, because you're taking it with respect to t, which there isn't a t in our equation. So like when we did implicit differentiation, there was x's and y's in our equation, so I knew what I was taking the derivative with respect to. But now I don't know that if I don't specify it. So, but this would be our dA dt. And then a lot of times I just change the color to write the answer in over here. And then I just box off that part of my answer when I do it. So this next one's another pretty common type of question that we have when it comes to related rates. So I am doing one off the practice page just because it's good to see. It'll be, the way that it's approached with the similar triangles will be similar to example 3, but it looks more like number 4. Anyways, it's just it's just different, so. All right, so we've got a man that is 6 feet tall, and he walks at a rate of 5 feet per second toward a street light that is 15 feet above the ground. So basically, I've got, would prefer my street light be straight, you know, with the ground. Okay, are we just not going to work today? What's happening? What is going on? There we go. So I got my little street light here. Don't judge my drawings. And then I've got my little dude.
He's 6 feet tall. He's not really little.
Well, you know what, Josh? I'm just kidding. He's over here. Wee. Is it a boy? A man. Okay.
I mean, if it was a boy 6 feet tall, then he must have had some early growth spurts or something.
Well, I just wanted to put a shirt on him.
It's a man.
Well, I'll put some pants too.
I guess that's better. No needs to be seeing all that.
I have some black hair. So I should make his arms a little longer. Wee. Pete. Okay. I'm being excessive.
Uh-huh.
I normally do a little stick figure.
Yeah, that's mine.
Yours is not very fun.
Now, I will also say, obviously there are different kinds of street lights. I'm making a slight assumption that it's this kind of a street light. They also have the ones that, you know, go straight up in the air and have the light on them up here. It doesn't really matter for the purpose of what we're doing. It's a street light.
Mine's
Okay.
like a Dum Dum lollipop.
Fair enough. All right, so I know that he is 6 feet tall. Which means that my street light is not proportional, but that's okay.
Not to scale.
I shall
Sounds
make
like
it better.
He's taking a shower and it's like butter pouring out of it or something.
He's like, sounds like one of those popcorn things at the movie theater. Butter.
I love those things. Yeah, you
All right,
push
there we
down,
go.
you can-
I made it a little better. Not much, but it's a little better.
I just wrote a note that it's not to scale.
Probably smart. All right, we know that the light is 15 feet above the ground. Now, I've intentionally drawn it from the light because depending on what kind of street light would be depending on, obviously the pole is higher than my light I just, the way I have it is what it is. So at what rate is the length of his shadow changing when he's 10 feet from the base of the light? So his shadow is over here. So I use a little S for shadow. So what I'm hoping here, there we go. I did it pretty good. It is. I'm almost going to make it like a triangle, essentially, from the base of the light. So at what rate is the length of his shadow changing when he is 10 feet from the base of the light? So obviously the base of the light is really over here, but they mean from down here. So again,
like not the light pole.
Right, from the light itself. So again, that's why it makes a difference which way you draw your light, but it needs to be basically under the light. So
Yeah, it's a dum-dum.
I've got X here. So things that I know.
Wait, what? Why is X? What?
I just drew it. I just don't have it lined up. The X is how far away he is
So he's
from the light.
10 feet away.
Right, so I'm getting ready to fill in here.
Okay, so
I
X
just
is-
didn't put, only numbers I put were those
so X
stationary
is
numbers.
10 feet. Oh, okay.
Yeah, that's what I'm getting ready to put here. Then S is here. dx dt. And ds dt. All right, so I'm going to draw this more as a triangle for the purpose of being able to see it a little bit easier. So we've got 15 here. I've got 6 here. This is S, this is X. So I'm looking at the big triangle versus this little triangle when I do my similar triangles. So I've got 6 over 15 equals S over S plus X. So that means that 6S plus 6X equals 15S. So six X equals 9S. I guess I could have also filled in. I know that he's walking at a rate of 5 feet per second toward the street light. Now, obviously, I'm making a little bit of an assumption here based on the direction, but it's walking toward the left. So that means that it's going to be negative. So negative 5 feet per second. Now, at this point, I could find S, but but I really I'm not going to need it because that's not actually getting plugged in. I would still say, because ultimately I'm trying to solve for ds dt because I want to know the rate that the length of his shadow is changing, I would get s by itself. So I would rewrite this as s equals 2/3 x. Now we take the derivative, so ds dt equals 2/3 dx dt. So that's 2/3 times -5. So ds dt equals -10/3 feet per second. Is the rate that the shadow is changing at. I don't need s, so I'm just going to put the x there. All right, then part B says, don't want to lose my little guy, my tall guy. At what rate is the tip of his shadow moving when he is 10 feet from the base of the light? What's the difference in this question and the previous one?
So, the previous one was asking at what rate the length of his shadow was changing, but this one is asking at what rate the tip of his shadow is moving.
Yep. So in this case, all I need is x plus s, right? Because I know how far he is from the light, and then the shadow is what's changing. So this is just x plus s. And then we take the derivative, dx dt plus ds dt. And then we use the numbers from up here, so I'm just not rewriting them. -5 plus -10/3. So will that be 15/3? -25/3. It's -25/3 feet per second. Because it was the rate that the tip of his shadow was moving, so all I cared about was the bottom part of this, which is the distance that he is away and the length of his shadow. And then we just take the derivative of those things, add those numbers together. All right, look at something here. So this next one that I'm going to have y'all just try to see if you can figure it out. I was going to give you the picture to go with it, or kind of give you. So basically we've got sand falling in a conical pile, and so we've got something like this. So this is the incoming sand. And this is the conical pile. So you'll use that to do those ones, and then the one about the boat will look more like the ladder problem when you go to do that one. So try for the last like 15 minutes to work through these few that you have as practice, and then tomorrow we'll go over theirs and look at a few from the book probably also, and then you'll have a few problems from the book. So no later than Friday for sure we'll wrap up this section.